This is Lab 3, Black Hole, by Nicholas Schweiker. So for the introduction in this lab, there are two main situations. The first is modeling a star orbiting a black hole in GlowScript. The second is modeling the trajectory of a ship taking off from a planet and going around a black hole. And then the purpose of this lab is to learn how to 3D model vector situations involving changing forces of gravity in GlowScript through implementing kinematics on a orbital mechanics scale. And then a preview of the lab is that for Model 1, the mass of the black hole is found to be roughly 1.9 times 10 to the 34th kilograms. And this is calculated through working the gravity equation backwards. For Model 2, the ship needs a minimum velocity in the y component of 1.9 times 10 to the 6 meters per second and negative 4.6 times 10 to the 7th meters per second in the x component in order to escape the planet's gravity well and slingshot itself around the black hole and not crash into either, so then it can then escape both of the planet and black hole's gravitational wells. So here are the main physics ideas. First, we have Newton's law of gravitation, where the attractive force between two objects equals the gravitational constant multiplied by their masses divided by the distance squared. Then we have Newton's second law, where force equals mass times acceleration. And then velocity update formula, where change in velocity is equal to acceleration times time. And then position update formula, where change in position equals initial speed times time plus half of the acceleration times time squared. So for part 1, the system is the star, while the surroundings is only the black hole. Initial conditions is star mass is 2 times 10 to the 30th kilograms. Delta T is 1 day, so that's interval between data points. And then starting time is 0. So here's the GlowScript. Starting at the top, we have the initial and final velocities, which are calculated previously. Then we calculate momentum with P equals mv, and then impulse, which is delta P equals m delta v. And then we define the rate of change of momentum and then set it equal to the net force. And then we calculate the parallel momentum and its rate of change along with the perpendicular momentum and then rate of change, and then set those equal to the forces. And then using that, we work the gravitational equation backwards to calculate the mass of the black hole. And then off to the bottom right, you see all the code for developing the visual arrows. So here are part 1 results. Off to the right, you can see the orbit of the star going around the black hole with the net force vectors going around in the parallel and perpendicular components. And then with that, we calculate that the average black hole mass is 1.866 times 10 to the 34th kilograms. So for part 2, the system is the ship, while the surroundings is the black hole and planet. Initial conditions, we have the black hole mass and then the planet mass, and then the planet starts into the plus x direction of the black hole, and then through trial and error, we chose the ship minimum speed that it doesn't crash, and delta t is 1 second. So here's the part 2 GlowScript code. So at the top, we calculate gravitational force on the planet by the black hole and then gravitational force on the planet by the ship. Use both those to calculate the net force on the planet. And then we calculate gravitational force on the ship by the black hole and then force on the ship by the planet. And then summing them, we get the net force on the ship. And then the position and velocity updates below for the planet and the ship with net forces and using the position and velocity update formula. So here are part 2 results. You can see off to the right, the ship goes on a successful trajectory, escaping the black hole and planet's gravitational well. It does not exceed the speed of light, so it does not break the law of physics. And you see the initial velocities where the x component is negative 4.6 times 10 to the 7th meters per second. The y component is 1.9 times 10 to the 6th meters per second. Although mathematically net force and rate of change and momentum are equal to each other, they are conceptually different. Force is from some external object or phenomenon causing an acceleration on an object, while rate of change is just change of momentum over time, and because momentum is related to velocity, it's related to velocity, while force is related to acceleration. And although they are conceptually different, as said before and proven mathematically, they are mathematically equal. So for the what if section of this lab, I successfully obtained an orbit for the ship around the black hole with an initial velocity of negative 3 times 10 to the 6 meters per second in the x component and 1.2 times 10 to the 7th meters per second in the y component. And this was found through trial and error, but it did create a successful orbit.